Section 3.9 discusses differentials. Differentials really offer us a useful and convenient way to estimate the change in one variable when another variable changes. So the nice part about this notation here is that we can think of these things as two separate quantities, dy and dx. So the condition is that dx can't be 0. Otherwise, obviously, we try to divide by 0, which doesn't work for us. All right? So let's take a look at the definition of a differential. We have some function y equals f of x, and the differential of x is called dx, and it's any real number not equal to 0. All right? The differential of y, we call dy, is given by dy equals f prime of x times dx. Right? And it's easy to see where we get that, because if we think about the different ways of writing a derivative, we know that one way we can do it is dy dx. Another way that we can write it is f prime of x. So we know dy dx equals f prime of x. And so to get this idea of differentials, we can multiply this dx to the other side, and we get dy equals f prime of x times dx. Right? Now we have to define this dy and dx and really understand what it means. So dx is just the change in x. So when we think about a delta x or a change in x, that's the same thing as dx. However, dy is not the same. Right? dy is approximately equal to the change in y. So dy is our estimate of the actual change in y, and we'll see. I think when we look at this graphical view, it'll make a little more sense. But dy, using this equation, gives us a good way to estimate the real change, which is delta y, of a function value when we go from one x value to another x value. All right. So the change in y, the actual change in y, is just one function value minus the previous function value. So it's literally just the change in the y value from one x value to another. Right? Take a look at this graphical view. And this also helps us see how we use dy to estimate the change in y. So we have some initial function here, and we know the slope of the tangent line here. We know the derivative. Right? So we can then move some distance horizontally away, and we move that delta x. That's the same thing as dx. Delta x and dx are exactly the same thing. But we move some distance away, and we might want to know how much did the y value change. So what is the change in the y value due to this change in the x value? Right? It's possible that this function is very complicated, maybe very difficult to assess or to evaluate. And so instead of actually reevaluating our function at the new function value, we use a tangent line approximation. So we use a linear approximation to a nonlinear function. And we say, well, as long as we stay quote-unquote close to the original point, then this tangent line approximation is a good approximation of the function. Now, how close is close? Well, that depends on a lot of things. It depends on how good does your estimate need to be. You can see that if I use the tangent line approximation just right here, it gives me a very good estimate of the y value. But if I get out here or even farther, it provides me with not a very good estimate of what the new y value would be. Right? So the first question is, how close do you need to be? And the second question is, how is the behavior of this function? This function is fairly smooth, so it gives us quite a pretty good estimate by using the tangent line approximation. But if this function came and curved back down this way really fast, then it would give us a pretty poor estimate of what the change in y was. So it also depends on how sort of smooth, or we call that well-behaved, the function is. But the end result is that we can calculate a dy quite easily just using the derivative times the dx and get the dy. So that's this distance here. And that provides us with an estimate of the actual change in y, which we may or may not know. And we may or may not be able to or want to find that, depending on how difficult it is to find. So let's look at a few examples here. So the first is just a real simple, find the differential of y, given that y equals 3x cubed plus 5. So I know that dy equals f prime of x dx. So in order to find the differential of y, I need to take the derivative. So dy dx, the derivative of this side is 9x squared plus 0. Now we just multiply the dx across. Here's our differential. This is the differential of y. In a general sense, this is the differential of y. Right? So this tells us here's the differential of y, and its value is going to depend on where on that function we start and how much we change the x value by. So remember that if you're asked for the differential of y, you're not always going to get a number like 0.1 or 3.2. You may just get an expression for the differential of y, and that's fine. Don't let that get in your head. All right, so here we're going to evaluate delta y and dy. So here it's really important that we understand the difference between those. Remember, delta y is the actual change in the y value. Right? dy is the differential. And it provides us with an estimate of what this actual change in y might be. This function is a pretty simple function, so we'll be able to find both. We'll find a differential that gives us a linear estimate of what the change in y is, and it's a pretty easy function to evaluate, so we can actually plug in the new x value and see what the actual y value is, and thereby get the actual change in the y value from one x value to the other. So let's do the differential first. So here I have dy dx equals 2x. I literally just take the derivative of that and then multiply the x over. So I get 2x dx as my differential of y. And now literally I just plug in what I know. I know the x value is -1. And I know that the delta x, the change in x, which is also the differential of x, equals 0.1. I plug that in. So dy is -0.2. So what that means is if I start at x equals -1 and I change my x value by a positive 0.1, I'm estimating that the change in the y value will be a -0.2. Let's see how that compares to the actual change in y. So the notation, don't get too hung up on the notation. Okay? The actual change in y equals the final function value at the new x value minus the original function value at the original x value. So we started at x equals -1 and we moved 0.1 to the right because this is positive 0.1. So that's all we're going to plug in. This is the original function value, f of -1, and then we moved 0.1 to the right, so now we're at -1 plus 0.1. So our new x value is -0.9. So we started at -1, we moved 0.1 to the right, and our new x value is -0.9. So we can plug those into x squared plus 1 and subtract, and if you do that, you'll find that the actual change in the value from f of -1 to f of -0.9 is -0.19. Right. So we can see here that is a pretty good estimate. Right? Why was it a good estimate? This is a pretty simple function, x squared plus 1. It's pretty smooth or well behaved, and we didn't go very far. We started at x equals -1, and our delta x was just 0.1. So we stayed relatively close to the original point at which we knew the derivative and where we started with the original x value. So that's differentials.